Hello everyone, my name is Jiayu Han from Illinois Institute of Technology. The title of my paper is Multi-Objective Optimization Model for Load Management in Island Microgrid. In grid-connected mode, the power can be transferred between the microgrid and the utility grid. When the load is larger than the total generation capacity of microgrid in grid-connected mode, utility grid can provide power and energy to the microgrid to maintain power balance. However, if the microgrid is in island mode and its total generation capacity is less than the load demand, it may cause frequency drop in microgrid. Load curtailment is the last resort to maintain frequency in island microgrid. Research has been conducted in an effort to solve this problem. The first step of research focuses on designing a load curtailment strategy to maintain frequency. The second area of research is to design an energy management strategy to determine the amount of load to be curtailed. The research initiatives are designed to minimize the total load curtailment, but they do not consider minimization of maximum load curtailment in one day. Maximum load curtailment is very important for microgrid future planning, demand response design, and the stability of frequency. Therefore, how to best reduce total load curtailment and the maximum load curtailment at the same time is a potential issue needed to be solved for the islanded microgrid. We propose a multi-objective optimal model to minimize the generation cost and load curtailment. For load curtailment, we not only try to reduce total load curtailment, but also minimize the maximum hourly load curtailment. The left part is a detailed equations of the proposed model. There are three parts in the objective function. Yellow part is to minimize generation cost. Blue part is to minimize total load curtailment. C1 is penalty coefficient to adjust the total load curtailment. The red part is to minimize the maximum hourly load curtailment. C2 is the penalty coefficient to adjust the maximum load curtailment. First, we analyze the impact of different coefficients. We compare the result of two cases which have different objective function for load curtailment. Case 1 is to minimize total load curtailment, while case 2 is to minimize maximum load curtailment. This figure shows maximum load curtailment of two cases. Black lines is the result of case 1 and red lines is the result of case 2. Case 1 has larger maximum load curtailment than case 2. For total load curtailment, the result of case 1 are smaller than that of case 2. So, considering different load curtailment have different results of maximum load curtailment and total load curtailment. Then, we analyze the influence of penalty coefficients and consider both total load curtailment and maximum load curtailment in the objective function. From this figure, we can see that there is a trade-off between minimizing total load curtailment and maximum load curtailment. We cannot decrease total load curtailment and maximum load curtailment at the same time. But this figure gives a guideline on how to choose C2 to satisfy different practical demands. In case B, we analyze the impact of penalty coefficient C1. We choose three different values of C1, and for a given value of C1, different values of C2 are used. We can see from the figures that if the value of C1 is large, the sensitivity to C2 is small, and only a big change of C2 can cause a change of a result. According to this case, we can choose suitable value of C1 according to different practical requirements. In conclusion, the proposed multi-objective optimal model provides a clear and straightforward method to reduce load curtailment that can be used in any system. Then we analyze the impact of different penalty coefficients of the two considerations of load curtailment on the final result, as well as the relationship between the penalty coefficient, which provides a guide on how to choose the penalty coefficient according to different actual requirements.